Hi, this is Stephen Rauer from Martin Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. And this is Stallings Chapter 5, looking at 3 topics. And instead of me reading them, let's just jump right into it. If I do this right, this will be short and sweet. Okay. Now a memory bank is a number of chips that are grouped together. And one of the things that actually, you know what? Hang on. I may not have actually done this in the overview video. Oh, shoot. Hang on a second. I don't think this video made it into the Chapter 5 overview. And what I do want to just point out here is that there's multiple chips here. There's 8 chips. And what each chip here will do in terms of the memory chip, it'll just store 1 bit. So the address that is being sent to this bank of chips, the address is being set to this bank of chips. The address is given to all 8 chips, and each chip is going to produce 1 bit. So instead of having 8 bits being stored on a single chip, there's 1 bit being stored on each of 8 chips. So for just 8 bits of memory, then this bank of chips will then produce these 8 bits, this byte. So sorry for that little offshoot there. So a memory bank is a number of chips that are grouped together. And in that picture I just went through, that was 8 chips that were grouped together for the producing of 1 byte. Well, the idea in interleaved memory is we can have multiple banks. And what will happen is if we have K banks, then K requests can be handled simultaneously. And so what some do is that between the different banks, if there's multiple, or I shouldn't say, if there's subsequent words that are being stored, the first word can go to the second bank, the first word goes to the first bank, second word goes to the second bank, third word goes to the third bank, and so that this way if a block of memory needs to be written or a block of memory needs to be read, then those reads and those writes can occur simultaneously if the banks, if the number of banks, if the number of bytes across the number of banks that we have matches the block size that is being read. That's interleaved memory. Okay. Prior to this point, the way that reads and writes were done in terms of memory is, well, asynchronously. So from the processor point of view, if it needed some data, what it would do is it would grab onto the bus where the memory is. So first have to make sure it's available, grab onto the bus, load the address lines with the address of the data that it needs, and then update the control lines to basically say, okay, I'm waiting for data. And then the CPU would either wait or go and do other work. The memory module would then realize, the control line is telling it to do, get something from memory. It would then look at the address lines and say, okay, let's go find the data. Let's load the data onto the data line. And once the data is ready on the data line, then it will assert a control line so that the processor knows that the data is ready. Once that control line is asserted, then the processor is made aware of, the data is now ready. Then it can go and start retrieving the data off of the data lines. And so what would happen is in asynchronous DRAM is that there wasn't a set time for how long it would take for the data to be loaded on the data lines when a read from memory request was made. Synchronous DRAM, then, it's coordinated between the processor and the memory when that data will be available. And so one thing, the processor will know exactly whether it's once a clock cycle or multiple clock cycles, it'll know exactly how long to wait before going and grabbing the data. So it doesn't need to look for a signal saying the data is ready. It will just, in so many clock ticks later, then just go and pull the data off of the data line. So that this way, in theory, yes, the processor is going to be waiting, but it's not going to be waiting a long time. It would be a small wait state or a finite. If the number of clock cycles is going to be large enough, well, the processor, if it knows it's going to be, I'm going to make up a number arbitrarily. If the processor knows it's going to take 4 clock ticks before the data is ready, well, for 3 clock ticks, it can do something else. That's what can happen. So synchronous DRAM is sort of a synchronization of using the clock between the CPU and the RAM so that the processor isn't really stuck waiting as long as it had in the past. And then double data rate synchronous DRAM, it's the same thing, but instead of just relying on the main beat of the clock, it actually can do it on the rising edge and the falling edge of the clock, and it has a higher clock rate. So it's still synchronized, it's just synchronized at a higher rate. And then the other thing is this buffering scheme can be used. So if you think of the processor writing data, if it's writing data faster than the memory module can store it, that the data will buffer, and then the memory module will catch up and then write the data out to the memory. And then the other way around, if the CPU has requested, let's say, a block of memory from the memory module, is that it doesn't have to wait for the processor. It can buffer up and sense that block of memory, and so that when the processor then is ready, it's grabbing that whole block. That's it for this piece.